My name is Aleksandr Popov. Today I will share my reflections on fuzzing from the bug hunter's perspective. And first, let me introduce myself. I'm a Linux kernel developer since 2012, and I'm also an open source maintainer of some projects related to Linux kernel security. And I'm a principal researcher at Positive Technologies, where I have fun with kernel vulnerabilities, exploitation techniques, and the most important, the defensive technologies which make the attacker's life harder. And I was a speaker at many international conferences for hackers and developers, and now I'm really glad to be here and to share my ideas with you. And first, I will give a short introduction to this talk. I've been thinking about fuzzing from the bug hunter's perspective for many years, and I always wanted to structure these random thoughts into something something more complete. And giving a talk and provoking a discussion is the best way to structure your knowledge. So that's why I decided to do this talk. At the same time, I found out that there are no talks about using fuzzing for vulnerability research, maybe because people tend to keep their know-how to themselves, not sharing secrets, but I decided to do that. So let's get started. And first of all, what fuzzing is? I am joking. I will not tell about that because every talk about fuzzing starts from this part. I believe everybody here knows that fuzzing is testing software with random inputs. But anyway, I will show you some funny pictures just to describe what I think about when I think about fuzzing. And first of all, I think about fishes which go up the river, and just like fuzzing inputs, which are covering the code and trying to get into dark corners of your system, the fishes do the same. And another idea is, when I think about fuzzing, is the gas effusion. It is the picture from some chemistry book. So in the upper side of this volume, there is a gas in high pressure, and there is a little tiny hole in the bottom, and some of the particles once upon a time can get into the lower part, but the same with fuzzing. The fuzzing inputs just hit all the code, and some of the checks can be bypassed once upon a time. That is how I think about fuzzing. And the last funny idea is about the Beatles fans. It is a historical picture with Beatles fans in Pittsburgh, and the fuzzing inputs just behave like them. They're trying to get through the security checks in your code, and I believe this fuzzing input is gonna crash the system. That's why we do fuzzing. We need to crash the system and find some bug which can. So, to summarize, fuzzing is a great way to delegate boring and really tedious software testing to the computers. But of course, you need to keep control on this process, otherwise it will not give any good result. And fuzzing is an instrument, and different people have different goals connected with it. So usually a software developer who use fuzzing, they use it for to search for bugs. And at the same time, the security researcher trying to discover vulnerabilities. Security researcher is not interested in all bugs that fuzzing can find. and that's how their goals are different. And usually, the software developer who is doing fuzzing for his project, has access to the source code, and that is not the case for security researcher. Sometimes security researchers have to do this black box fuzzing when they just have binary and nothing else. And usually, when developer is running fuzzing against the system, he or she enables all the debugging mechanisms in the target system to see all the crashes. But security researcher behaves differently because security researcher is interested in vulnerabilities, the bugs which are in the attack surface. And moreover, security researcher wants to find the bugs which can be reproduced easily and stable in a stable way. That's why the way they use fuzzing is different. And moreover, security researcher, everybody who participates in bug bounty knows that when your bug is duplicated, it is very painful. And that's why security researchers usually want to find unique bugs, which others don't find. It is an interesting aspect that we will cover when we describe how to use fuzzing for vulnerability research. Okay, so now the main question of the talk. What is really special about fuzzing for vulnerability discovery? And to be precise, I will use my favorite kernel fuzzer to speak in some technical details. It is called Syzkaller. Many people know it. It is the fuzzer for kernel. Operating system kernels. It supports Linux, various microkernels, even Windows, and I use it for several years. I like this project, and I like people who develop it. And today I will describe how it works and what to do in this kernel fuzzer to make it find vulnerabilities. Okay, now this picture, it has tiny text, so I will zoom into it and describe you how this fuzzer works, and then I will describe what is different for vulnerability research. So I will zoom into. First of all, I would cover the part which is the main part of the fuzzer. It is implemented. The fuzzer is called Syzkaller, and the main logic is implemented in Sysmanager. This component is responsible for starting, stopping, managing the virtual machine where kernel fuzzing is going. And Sysmanager works with so-called corpus, the database with programs which are used for random testing. And so Sysmanager adds and removes new fuzzing inputs to the corpus. The fuzzing inputs are described in a special language. Every structure-aware fuzzer has to know the semantics of the data which it uses for fuzzing. And if we speak about kernel fuzzing, the Syzkaller needs to know what the semantics of the system calls. So Syslang is the special descripting language that describes the system call anatomy. For example, we have a system call write. The first argument is the file descriptor. Second is the address of the buffer, and the third is a size, for example. So Syzkaller needs to know how to work with the arguments of the system call. And Syzkaller has the configuration. It is it has various modes of working. So I will further I will describe what can be customized in this configuration. And when the kernel crashes, those events, the kernel oops, are collected to the crashes base, and some of them have the reproducers, the shortest program that can provoke this crash. Now, going to the part of fuzzing inside the virtual machine. The virtual machines contain the Linux kernel and the part in the user space. The Linux kernel is the part where we are for bugs, yeah, and that's why it has some debug features and so-called sanitizers. Those are special technologies which make kernel crash if we have some, for example, use after free vulnerability or out of bounds vulnerability. It is awesome part, and vulnerability researcher enables those checks which can show that some security relevant event happened in the kernel. And when the virtual machine starts, the sysmanager connects to via SSH and launches the sysfuzzer process. It is the main process which works inside the virtual machine and responsible for fuzzing. And this process uses so-called sysexecutor to call the system calls. Yeah, and every modern fuzzer which has high performance, I would say, has so-called coverage-based feedback. So when the system call is called, kernel code handles it, and there is a special technology called kernel coverage. It is compile time instrumentation of the code. It is responsible to get the information which basic blocks inside of the Linux kernel were executed. And these statistics of the coverage goes back to the sysmanager, and that's how the sysmanager decides what fuzzing inputs are very interesting to mutate kind of evolution algorithm. So the fuzzing inputs which get more coverage in the kernel are taken for new mutations, and that's how fuzzer goes deeper inside of the code. Yeah, so there is a basic architecture of the Syzkaller kernel fuzzer, and now let me dive into the security relevant part, how to make it find not bugs but vulnerabilities. But first of all, I want to talk with you about the hardware. It's an important aspect. Everybody who does fuzzing for research, when they meet together with beers, for example, the first question they ask each other, and which hardware do you use for fuzzing? It is a very interesting aspect. So I want to speak about that a little bit. First of all, as I told, the fuzzing goes inside of virtual machines. That gives us the requirement of hardware virtualization. So usual virtual private servers in usual cloud providers don't have the virtualization enabled. That's why we have some limitations. The only one VPS which provides hardware virtualization is Google Cloud Engine, and it is not available in all countries. So if you can't use it, you have to work on dedicated server because you need hardware virtualization. At the same time, the dedicated server has really unusual characteristics for fuzzing. Why? First of all, security researchers know that for fuzzing you need as many CPU cores as you can, because in our case the number of CPU cores limits how many virtual machines we can start simultaneously, right? So if your server has very modern multi-core CPU, it is better for you. And the volume of RAM is not so limiting because we only need a number of virtual machines is CPU number divided by 2, and virtual machine 4 GB of RAM. So it would be a server with a very good CPU, but not so big amount of RAM. That is strange because usually it is vice versa. And moreover, on this server, we don't need a really huge hard drive unless we use the tracing or snapshots for fuzzing. For example, on my server, which has 64 CPU cores and 256 gigabytes of RAM, for kernel fuzzing, it needs only around 200 gigabytes of disk of hard drive, not so much. So it brings to the result that if we have a dedicated server, it should be in some special customized configuration. Otherwise, we will overpay if we just go to the cloud provider and ask for a dedicated server from them. Okay, so that's for the hardware part. And now about the software. Once again, our goals is not to find bugs, but find all bugs via the accessible via attack surface. So vulnerabilities. It is the first point. The second point is that we are interested in bugs with stable reproducers, not some random crashes which you need to try to provoke for a week. It is not interesting. Just instant memory corruptions, for example. It is much more interesting for the vulnerability researcher. And third, as I said, we are interested in unique bugs, not to have dupes with other researchers. And I will cover all of these 3 steps. And first of all, we're interested in vulnerabilities. Which kind of vulnerabilities do we have for operating systems? 2 kinds of them. First is local privilege escalation, LP. When we have an unprivileged user on the system, it runs the exploit and becomes root or administrator. And the second type of vulnerabilities is remote code execution. When the system has some, let's say, network interface, and remote user provokes some activity in the kernel, which makes it gives him in the kernel. I will zoom into once again to show you. So first, for the local privilege escalation. For local privilege escalation, the only modification of fuzzing which we need to do is simple. Just start sysfuzzer not from root, like in stock Syzkaller, but launch it as unprivileged user. In that case, the sys executor will call system call from the unprivileged user, and so only the LP attack surface will be fuzzed. It limits the scope and gives us only security relevant bugs. And as for remote code execution, it is more interesting. As I said, remote code execution needs interaction via network from outside. But this Syzkaller kernel fuzzer, it emits the system calls. How to make it work? And my friend Andrei Konovalov, who is one of the developers of Syzkaller, wrote a wonderful article. I will publish the slides. You will manage to follow the link. He gave the overview how he developed the network fuzzing inside the virtual machine. The idea is, I think, quite simple and elegant. So there is some special virtual network interface in the Linux kernel called TuneTap. It is the network interface which you use when you run VPN, for example. So all traffic is encapsulated when you send it through this interface. And Andrei wrote a special so-called virtual system call called sysemit Ethernet. This system call allows you to inject network packets through tune-tap interface, and they get into the network stack of the Linux kernel. So the remote code execution attack surface is fuzzed using this thing. And if you want to fuzz only for remote code execution, the only thing you need is to allow in the Syzkaller config only system call sysemit Ethernet and some other needed system calls, and you will fuzz only the RCE attack surface. Nice. So that is how we solve the first problem: how to find not bugs but vulnerabilities. Yeah. Second one. As I said, we need to find bugs which have stable reproducers, and Sysmanager has some logic inside of it. When Sysmanager detects some virtual machine is dead, the Sysmanager knows which chain of the system calls was called to provoke this crash. But usually this chain is very, very large. It has several thousand of system calls, for example. And what Sysmanager is doing, it is trying to minimize the reproducer which was used to provoke this crash. So like those binary search, you try the first part, the second part. If second crashes the kernel, you divide it by half once again and do it once again. And finally, Sysmanager finds the minimal reproducer which provokes the crash. But sometimes it doesn't work. Sometimes it gives the false positive errors and false negative errors. For example, in some cases, Sysmanager, during the minimizing the reproducer, doesn't manage to provoke the crash again because there was some race condition which was missed when we dropped some system calls. And Sysmanager says, "Okay, I can't. So no repro for this crash." It is a first kind of bug. Another kind of bug is sometimes Sysmanager, the chain of system calls breaks the Syzkaller inside the virtual machine itself. So it was not a kernel crash, but the virtual machine didn't reply because the sysfuzzer dead. And we are not interested in such cases as well. So to solve this problem with not stable kernel crashes, usually researchers implement a separate logic. I will zoom again to make you see it. So the researcher implements some separate logic for triage and filtering of the crashes. So there is in Syzkaller fuzzer, there is a separate tool called sysrepro. You can give it the list of the system calls, and it will try to reproduce the crash and minimize the reproducer. And you can run this tool very, very many times until you get the success. So if you want to filter out the crashes and drop those which are not stable, you can implement it in this logic and just call the sysrepro the way you want and don't rely on to default Sysmanager behavior. Okay, so that's how to make that's how to filter only the crashes which are stable. Okay, yeah, and now the most interesting part, and it is the main slide of the talk. I will focus on it for some time. How to find the bugs which are unique, which are not, which other researchers didn't find. As you see here, I colored in red the parts of Syzkaller which should be modified to find unique bugs. As you know, if you want to find something unique, you should use unique instrument. You can't find unique things when you use the same instrument that your competitors use. That's why you should do something different to find unique vulnerabilities. And the first idea how to make it find unique bugs is to limit the enabled system calls, which Fuzzer calls to the Linux kernel, to limit them in the Syzkaller configuration. You can say, okay, I'm interested in a specific attack surface. I want only the system calls which interact with this service, and I'm not interested in all other. That limits the fuzzing, the area in the code which you fuzz, but time it makes fuzzing go deeper. It just don't spend time to uninteresting parts. It only spends time on to fuzzing your attack surface. So it is a really nice way to compete with Sysbot, which is the Syzkaller instance run by Google, which is fuzzing the Linux kernel all the time. So if you want to compete with Sysbot, just limit, make your fuzzing area more narrow, and you will go deeper. Okay, it was the tip number one. Another way to really nice way to find new bugs is to write new descriptions in Syslang. As I told you, Syslang is the specific language describing the semantics of the system calls. And if you find, for example, some system calls in the Linux kernel which are not covered by Syslang descriptions, that means that the Syzkaller fuzzer doesn't test this part of the code. And you can find new bugs if you just describe how system calls can be used there. A lot of Linux kernel vulnerabilities which researchers publish were found using this trick. Okay. Very interesting. In user space, there are a lot of fuzzers like libfuzzer, IFL, and all of them, and they compete between each other. And the aspect which they like to compete is the mutator. How the inputs which are interesting for you should be modified and added to the corpus to get new coverage. And if you want to find unique bugs, you can just modify the mutator. It will change the corpus a different way, not like others, and you will find new unique vulnerabilities. And there is a dream in the Linux kernel security community is to implement the symbolic execution for Linux kernel fuzzing. The symbolic execution can make your fuzzer much more clever because, for example, if in some kernel code you have the condition like if some variable equals to 42, then some logic is implemented. And it takes the usual fuzzer a lot of effort to generate the input which has this 42, this magic number. But at the same time, the symbolic execution engine can just generate the needed input depending, just looking at this kind of condition in the code, and put this into the corpus. And your kernel fuzzer just instantly get deeper into the code and get new coverage. So symbolic execution for Syzkaller takes some effort, but I think sooner or later it will be implemented. Yeah, number 3. Number 4, another nice idea how to find unique bugs is to start from unique corpus. So it is corpus with the interesting inputs, which will be taken as the seed of for fuzzing, and will that unique corpus and find the bugs which others don't find when they start from the empty corpus. Nice idea as well. The trick number 5, where is it? Yeah, it is the Linux kernel. I like this. Sometimes for the Linux kernel, we have the source code, and sometimes when you change the fuzzing target, you can make it more convenient for the fuzzer. And the fuzzer can get new coverage just because you modified the target. And that is how I found this 0-day, which I exploited and did responsible disclosure. It was funny bug. It was hidden behind the kernel warning. So other kernel fuzzers only found the warning, but I modified the Linux kernel and disabled. I just dropped all the warnings. And behind the warning, there was a use after free bug, which I managed to exploit, get local privilege escalation and fix. So if you modify the target somehow, your fuzzer might become much more effective for this target. Nice idea. The next one is it is the number 6. Just use more power than your competitors. If they use one server with 64 cores of CPU, use 10 servers, and you just get more bugs. But there is the downside of this trick, because you need to handle all the reports which Syzkaller gives you, and if hardware computing power scales, you don't scale. That's pity. Yeah. Another interesting idea how to find unique bugs is to change the rootfs. That might sound strange, because the kernel image, I say, the file system image for your virtual machine doesn't really directly influence the kernel. But it was how I found my another 0-day, which I exploited and then fixed. It was funny. It was my first experience with kernel fuzzing, and when Syzkaller just creates the rootfs using the so-called debootstrap tool, I did another way. As a newbie in this area, I decided, okay, I want to create the rootfs for normal Ubuntu, like the real system which you install to the server or laptop. And I put all the built kernel modules inside this rootfs. And when my kernel fuzzer called special system call, it created virtual terminal with special line discipline, the kernel module in the rootfs was automatically loaded. And my fuzzer found new vulnerabilities which were not found by Syzkaller, because I just put the needed module into rootfs which was auto-loaded. That was nice. It was just a good luck, but anyway, it is a nice way how to make your fuzzing setup look different from others. Another interesting approach is, I would say, from all of them, it is the more technical one. Implement new sanitizers or debug features. That's interesting. In the kernel, you have memory, so-called slab allocators, and sometimes some kernel subsystems have special allocators inside slabs. So usual sanitizers only find memory corruptions in slabs. But if you develop a new sanitizer which can find those memory corruptions, out of bounds access inside of the object, you will find those bugs which are not covered by anyone, because you just created new detector of the bugs. That is interesting, high technical approach. I like this idea very much. Another one is in user space fuzzing. It is called directed fuzzing. When a fuzzer somehow limits the scope, the scope of the code which it tries to test. And for Linux kernel, we can do the same. We have two ways to do that. First way, we can modify the kernel coverage. We can just for example, build some interesting part of the kernel with coverage and all of others code without coverage. In that case, when fuzzer tests the kernel, the inputs, the syscalls without coverage, just ignored because they don't make the coverage grow. But only the part which you are interested in have the increase the coverage counters, and that's why the sysmanager only takes interesting inputs and directed fuzzing using this. Another approach, there is a special feature in the Syzkaller config file called cover filter. So you can collect all the coverage from the kernel, but say, I'm interested only in this specific subsystem. And the fuzzer will just throw away all the other not interesting inputs. And that will make, like in the first approach, fuzzer go sharp into the interesting subsystem. Yeah, so summarizing, if you want to find unique bugs, you should make your setups unique. And there are several ideas which I, in the first day of Positive Hack Days, I have organized the open discussion on this topic, and some of these ideas were taken from this discussion. So I think exchanging the knowledge, not sitting just on own secrets and know-hows, it is how our industry can move forward and become better. Yeah, and to finish the talk, I really love fuzzing. I think it is a wonderful research instrument, and moreover, it can be used not only for searching vulnerabilities, but at the same time, it is the thing which I'm proud, I'm glad about. Using fuzzing, I discovered the MSG heap spraying primitive, which is used by a lot of researchers all over the world. So it was how I found it in 2021. When I found some zero-day bug, I was trying to, it was used after free in the Linux kernel, I was trying to exploit it, and I needed the heap spraying primitive, the way how I should do some action in the user space to make the kernel allocate at the same position, to override the freed object. And I was reading the source code for a week. It was a very exhausting experience, and I thought, okay, let computers do their job. I added the bug condition onto the Linux kernel allocator, slab allocator, and made it report me the interesting object which I wanted. And I just started fuzzing with this type of a bug. And once upon a time, fuzzer found the interesting object which I wanted. So I just explored the kernel code using the fuzzing approach. So it is a nice instrument which you can use not only for vulnerability discovery, but it's an everyday practice. As I say, it's like mining gold. You just do it every day, and sometimes it's very exhausting. Sometimes you just understand, I have a lot of crashes, I can't handle them, I should filter them somehow. Or sometimes you just find the crash, find the crash, and all of them are not interesting. And I understand, okay, maybe I'm searching in a wrong place. Maybe I need another attack surface. So sometimes it's exhausting, and sometimes it's you just get disappointed because you just put a lot of effort. As I say, you need to be brave because you are risking all the time. You risk your efforts. You risk the computing power used for fuzzing, and but at the same time, it is so exciting when you eventually get success. And here I have this small asterisk. It reminds me to tell you one short story at the end. Once upon a time, I had a nice conversation with a person, and I told, you know, development is much more easier than research. Because when you develop, you just write code, and when you finish, you just have the success because the code is written. You just feel, well, everything is fine. But for the research, you may do something for months and get no result at the end. It's so risky and disappointing. But he said to me, when you are a developer, you work with the code. But when you are a researcher, you will work with the ideas. It's different. And if every idea is excellent and good, that means that every idea is cheap. But you need really expensive, really good ideas. So that's why you risk, that's why you fail, but that's how it works. So let's do research. And
Thank you very much, Aleksandr, for sharing your secrets about fuzzing. So any one of our audience have questions for this talk? Okay.
Thank you so much. I have never fuzzed before, but it's very interesting. How long did it take for you to fuzz and find your first vulnerability?
For the first vulnerability, it took me like 3 weeks.
3 weeks?
Yeah, but as I said, it was kind of luck. I don't know. It is like mining gold. You just start digging and you never know. But there was another part of my career when I was doing research for 9 months and didn't get to success. And then after 9 months, it was so exhausting. I just found it. It was I was very glad to do that. But 9 months, of course, I was doing that part-time. So I have, at my job, I have a lot of organizational tasks and management tasks. And I do research part-time. But anyway, when you do something for many months and don't get a result, you feel the pressure. So maybe I would recommend you to start doing it part-time, not to feel disappointed when it doesn't work, but slowly and steadily get the experience, and then you will find your first interesting things. And another aspect, I would recommend you to start from fuzzing the open source projects, Linux kernel, some open source libraries, and so on, because it allows you to do the full life cycle of the vulnerability. You find the bug, you try to understand its exploitability, then you report it. Finally, if it is open source, you can create a patch which fixes it and provide this patch, and it is merged to the upstream. So you did all of the cycle, and then after the patch is merged, you can think about some technique or mechanism which would mitigate this kind of vulnerability or attack method. So you can do all of the types of the research if you work with open source, starting from offensive, ending with defensive, and it is very rewarding. I would recommend to do that. Yep.
I also have another question. Actually, it's from my friend. I know that we know that fuzzing takes a long time to get the result, but how do you know that you have set up correctly and it's working correctly? Because we don't want to fuzz for like 4 months to find that we set up incorrectly, right?
Yeah.
How do you debug it?
Absolutely. Very good question. You can control the coverage during fuzzing. So Syzkaller provides you the overview of the coverage which was collected during fuzzing, and you can see how it grows. And if it doesn't grow for some reason, you can debug that and understand. Okay, here I had the wrong setup. I should fix it and see how the coverage grows again. So the main thing to debug fuzzer is the coverage. Yeah.
Thank you.
Thank you.
Are you ever disabling any mitigations when you're fuzzing for like efficiency reasons, or are you relying on some of the mitigations to actually detect crashes like SMAP, for example?
Right. Good question. Thanks. It is a trade-off. So if you enable some debug features, you will get more crashes. At the same time, the kernel becomes slower and the fuzzing process goes slower. At the same time, when you have a lot of debug features, you have a lot of crashes and you may not be interested in all of them. For example, you are not interested in warnings. You are interested only in memory corruptions. That's why you should disable warnings, not to give attention to them at all. But you should, for me personally, when I enable debugging, I try to focus only on those kernel errors and those events which are interesting from attacker's point of view, because other technology are not just give no noise, but not interesting for me from security research perspective. And another interesting aspect is fuzzing without debugging at all. Why? It is the idea which I got 2 days ago at Positive Hack Days, discussing with a person. That's amazing. I didn't know that. But if you fuzz the target without debugging, it is very fast, but you get the coverage anyway. So the corpus is filled by new inputs. They are mutated. And later, when you just collected a very big corpus, because you go very fast, you can enable the debugging features and see whether this corpus with all those inputs give you crashes. So you can combine them and get interesting results. Thanks.